Welcome to the final presentation for Team 35. Our group members are Mahmoud Haj, AJ Kraus, Brady Nordbeck, Henry Persons, Lark Sawyer, and Audrey Safer. Today we will be discussing our analysis and redesign of a particular model of food dicer, starting with a recap of the work presented in the interim presentation. As depicted in the clip on the slide, this food dicer divides solid food items into smaller sections in two steps: vertical slicing and horizontal dicing. We have identified two customer groups that comprise a total estimated U.S. demand of 11.5 million. For this project, we consider a production volume of 50,000 units for the primary customer group of restaurants. The initial product design is comprised of 14 parts of 10 unique geometries. The food dicer has two primary basic functions: direct food and cut food. These functions are divided into sub-functions with the diagram's terminal branches highlighted here. These terminal functions are used to create a functional component mapping matrix that categorizes the product components based on functional importance. A product family has been designed with a variant for the identified secondary customer group by determining which product functions are different in each customer group and correlating the functions to shared platforms and variant module components. In our product family design, the frame, channel, and top presser shown here, as well as the entire linkage system, act as platform components. The frame includes the common sliding interface that supports the grate and back presser modules. Looking closer at the module design, we observe the biggest difference in the grate, which is a heavy-duty box for the primary variant and two lighter-weight halves for the secondary variant. This difference in size induces a need for slightly different sized back pressers in each variant. And we developed an assembly sequence for the product family that adds the grate variants later in the process to achieve delayed differentiation compared to the original sequence.
To lower the assembly cost for the food dicer product family, we selected one platform component, one primary variant module to redesign for manual assembly. We chose the handle as a platform component to redesign due to its high functional importance as identified as the FCMM, as it contributes to 6 of the product's total 12 functions. While the handle is classified as low cost compared to the other product platform, the redesign presents an opportunity to consolidate the handle with the short rod that passes through its center. This will largely reduce overall assembly time and cost. In doing so, replace the short rod with a snap fit on either end of the handle, allowing the bent linkages to connect directly while still enabling relative rotation during the food dicer operation. The new design maintains part symmetry and easy alignment while capitalizing on the assembly efficiency of snap fits over other fasteners. Given that the overall part geometry has changed very little, minimal impact on component function and manufacturing cost is expected. We chose a back presser as a primary variant module to redesign as it is tied for the highest assembly cost. It is also classified as highly functionally important to the FCMM as it contributes to 5 of the product's total 12 functions. While the back presser was classified as low cost, it includes features that can be improved for easily handling compared to the other primary variant module, the grate. Comparatively, the assembly difficulty for the grate is a result of the difficult handling due to the grate's weight and the danger posed by the sharp slicing blades. These features of the grate are inherent in the component functionality and cannot be designed out. The back presser is easily redesigned to increase part symmetry, which reduces beta from 360 to 180 by centering the hole for the long rod. Part insertion is improved by adding chamfers at the interface between the back presser, the frame, and the long rod. Overall part geometry has changed negligibly, so little impact on the component function and manufacturing cost is expected. Part redesigns result in an overall reduction of assembly time by 18.28 seconds and assembly cost by 36 cents. The assembly efficiency improves from the previous 31.39% to 37.35%.
We selected 3 small lightweight parts to redesign for automatic assembly: the small link, end cap, and long rod that passes through the frame and back presser. Using our function component mapping matrix and quad chart, we identified the small link as an important part to redesign given its contribution to 5 out of 12 functions. The end cap and long rod were additionally chosen as they form a subassembly of platform components. Despite its classification as low cost, we recognize the opportunity to consolidate the small link and the end cap into a single part, therefore achieving DFA 1 and reducing assembly cost. The small link is designed to include a cylindrical feature that can be fed through the bent linkage and hammered to fix the parts together without requiring an additional fastener. Furthermore, incorporating a bend into the small link enabled us to reduce the length of the long rod to match the length of the short rod. This change allowed us to fulfill DFA 5 and standardized part lengths, avoiding future confusion when sorting parts during the assembly process. To accommodate our new design into the full product assembly, we widened the tracks on the frame to avoid interference between the frame and the new end cap feature of the small link as the linkages move during the dicing process. This simple alteration does not dramatically affect assembly time or material cost. While the redesign sacrifices the multi-axial symmetry of the original small link, the benefits of part consolidation and standardization outweighed any increased costs. The redesign reduced assembly cost by 4 cents, establishing the small link as the cost-effective solution that still achieves the functions of the original part.
Our considerations for design for manufacturing include the analysis of 2 key functional components, the small link and the handle. Our small link, as it was redesigned for automatic assembly, is shown here with key dimensions. All dimensions follow tight tolerances as low as plus or minus 0.03 millimeters to ensure proper functionality of the linkage assembly. We created this process selection table to choose a manufacturing method for the small link. All casting methods of the aluminum small link fail due either to the mass, shape, or section thickness of the redesigned part. We've delayed the process down selection for tolerance to the final metric, as this is the area that we have the most control over in design. After completing the chart, we selected machining as our top choice, with powder methods as a close second. Ultimately, we dismissed powder methods due to the necessity of opening up part tolerances to a minimum of 1 millimeter. This increase would bring part tolerance too high, potentially interfering with the part's intended functions of guiding and dicing food. Before implementing redesign for machining, the part is estimated to cost $557, with face milling being the most expensive operation as shown in the table. Following design for machining guidelines and the suggestions from DfM Pro, small radii were added to internal corners, chamfers were added to external edges, and the link was widened to allow for proper machining tolerances and fitment within the machine fixture. Here are the dimensional changes made to the design to implement these suggestions, again with a wider part and more rounded lead-in features around the riveting cylinder. These modifications slightly increase our part cost to $619 as shown in the table, but also simplify the machining process. Performing a part cost analysis using Protolabs network by hubs yields the same result, with part cost jumping from 63 cents to 93 cents, likely due to extra material cost from widening the part width. This discrepancy between the analytical estimate and the quote from hubs is likely due to the far extrapolation of batch size from 1,000 to 100,000 parts.
We further used our process selection methods to analyze our redesigned handle. The redesign includes a rod and snap fit ends that connect the handle to the bent linkages. The 10 millimeter radius of the fillets of the knobs is a key dimension given its interface with two parts. This dimension has a tolerance of plus or minus 0.15 millimeters, the recommended tolerance for close snap fits. In addition, the overall length of the handle is 249.3 millimeters and has a tolerance of 0.5 millimeters, ensuring that the bent linkages attach at the correct distance when incorporated into the dicer assembly. We used the process selection table to evaluate which methods would accommodate our redesigned shape, mass, thickness, tolerances, surface finish, and economic batch size. Most methods failed immediately given the handle's circular shape. However, both machining and injection molding ended up being options for building our design. Because our batch size is large, injection molding will likely be much cheaper than machining. Thus, we selected injection molding to build the handle. Cost estimation for injection molding the handle was then conducted. The cost per part ended up being over $271, with the majority of the cost coming from the operating cost. This is in large part due to the handle diameter being nearly 4 inches, causing the cooling time to be over 3.5 hours. Following DfM guidelines and the suggestions from DfM Pro, the diameter of the handle was lowered to 1 inch and the shape was simplified to a cylinder. Snap fit knobs were also converted to an annular shape to lower mold complexity and alleviate an issue with the gap between the two snap fits being too small. Fillets were also added to increase the draft angle on multiple edges. Alternate views of our redesign, as well as key dimensions and tolerances, can be seen here. After the redesign passed all DfM Pro checks, another cost estimation was conducted. Our redesign reduced both manufacturing and assembly cost estimations for the handle, with the manufacturing cost dropping to just under $9 per part. This reduction allowed for an overall cost decrease of over 96%, with the majority of the reduction coming as a result of the decreased diameter, ultimately dropping cooling time by 93%.
In addition to the two product variants, we plan to offer a part replacement service. The service would consist of a program that accepts and recycles damaged parts and ships replacement parts for the dicers upon the customer's request. The service aims to improve the customer experience by allowing repairs to existing products without needing to purchase an entire new model, as well as to reduce the negative impact on the environment by recycling used parts. For the redesigned parts, the small link and the handle, the combined manufacturing cost was reduced from $277.39 to $15.18, a 94.52% decrease. The assembly cost was reduced from 62 cents to 51 cents, creating a 17.74% decrease. In total, our redesigns result in a cost reduction of $260.96, a 93.86% decrease. Our redesign successfully improved the cost and efficiency of assembly for the food dicer by following the principles of design for manufacturing and assembly. Benefits of our redesign include part consolidations that resulted in a reduced total part counts, as well as a reduction of the number of unique parts, allowing for improved assembly times. Additionally, our redesigned product mainly consists of platforms, allowing for better delayed differentiation while maintaining varied functioning across the product family variants. Although we implemented many positive improvements to the dicer, some design elements still negatively impact manufacturability. The great and large frame are still high cost and difficult to assemble. And although some part redesigns improved assembly efficiency, part cost was increased. If we were to repeat the redesigning process, we would enact additional changes, such as the integration of the short rod into the frame to improve assembly and farther reduce the number of parts. We would also have considered farther adjustments to the back and top presser design to allow for more similarities in size and farther delayed differentiation and decrease manufacturing costs.